Have you ever really truly thought about what it means to move? Going from point A to point B seems so simple, but to describe it with a real precision, well, that's an art. And that art? It's called physics. But don't worry, this isn't about scary equations. It's about learning the language we use to describe our world in motion. So you ready to dive in? Let's get started.
All right, to get our brains warmed up, let's start with a little puzzle. Imagine an athlete runs one full lap on a truck. They're back at the starting line, probably out of breath. They've definitely moved, right? But in the language of physics, what is their displacement? Just hang on to that thought for a minute. The answer might not be what you think.
So, to crack that puzzle, we need to get crystal clear on two ideas that sound alike but are actually worlds apart. I'm talking about distance and displacement. These are like the first two essential words in our new language of motion.
Okay, first up is distance. This is the one we all know and use every single day. It's the total ground you covered. Every step, every detour, the whole shebang. It's what your car's odometer tracks. We call it a scalar quantity, which is just a fancy way of saying it's a number, that's it. 400 meters, 2 miles, no direction, just the raw length.
Now, displacement. This is a whole different animal. Displacement doesn't care about the scenic route you took. Nope. It only cares about two things. Where did you start? And where did you end? It's the straight line, the as the crow flies path between those 2 points. And because it includes direction, we call it a vector. It's not just 5 kilometers, it's 5 kilometers to the northeast. See the difference?
Okay, you see where this is going, right? Let's get back to our athlete. They ran a full 400-meter lap, so their distance is 400 meters. But because their starting point and their ending point are the exact same spot, the straight line between them has no length. So their displacement is a big fat zero. In the eyes of physics, they went nowhere. And this idea works even when you don't end up back where you started. Look at this example. A boy walks 3 kilometers east, then hangs a left and walks 4 kilometers north. The distance he walked? That's easy, right? 3 plus 4 is 7 kilometers. But his displacement? That's the straight shot back to the start. A little geometry tells us that's only 5 kilometers. Same trip, 2 totally different measurements. So let's just lock this in. Distance, that's the total path you took. It's just a number, a scalar, and it's always adding up. Displacement, that's the direct line from start to finish. It's a vector because direction matters. And as we just saw, it can be 0 even if you've run a whole marathon. Okay, we've figured out how to describe where you went. Now let's talk about how fast you are going. And you guessed it, just like before, physics has 2 different ways to talk about this: speed and velocity. You're going to see that same pattern here. A simple number versus a number that also has direction. And the connection here is just beautifully simple. Speed, the number you see on your speedometer, is tied directly to distance. It's just how much ground you cover over a certain amount of time. Velocity, on the other hand, is tied to displacement. It's not just how fast, but also in what direction. So speed is our scalar and velocity is our vector. Simple as that.
Now, here's where it gets a little subtle, but this is a really key point. At any single instant in time, like right now, the number for your speed is exactly the same as the size, or what we call the magnitude, of your velocity. So if your car's speedometer says 60 miles per hour, your instantaneous speed is 60, and the magnitude of your velocity is also 60.
But, and this is a huge but, when you zoom out and look at an entire trip, things can get really weird. Your average speed, which is your total distance divided by time, can be completely different from your average velocity, which is your total displacement divided by time.
Let's bring our track star back one more time. Let's say they ran that 400-meter lap in 60 seconds. Their average speed is pretty quick, right? About 6.7 meters per second. But what's their average velocity? Well, remember, their total displacement was 0. So their average velocity is 0 divided by 60 seconds, which is 0. Pretty wild, huh?
So we've got position, and we've got the rate of change of position. But what about changing your rate of change? Well, that's acceleration. And most of us think of acceleration as just speeding up. But in physics, it's any change in velocity. And that tiny difference in definition leads to some really surprising stuff. So get this. Here's a statement that just sounds wrong. A positive acceleration can actually mean something is slowing down. I know, that totally goes against how we use the word every day. You hit the accelerator in your car, you go faster. So what on earth is going on here?
Yeah, seriously, how is that possible? How can adding something positive make you slow down? Well, it all goes back to that key idea that velocity isn't just a number, it has a direction. Okay, let's break down this graph. The vertical line, the y-axis, is velocity. Notice how the line starts down in the negative part of the graph? That means our object is moving backwards. But look at what the line does over time. It's moving upwards, towards zero. That upward slope is a positive acceleration. So the acceleration is positive, but it's fighting against the negative velocity, pulling it back towards zero. And that means the object is slowing down. So really, you can forget all the confusion and just remember this one golden rule. Just look at the signs. If velocity and acceleration have the same sign, if they're both positive or both negative, they're on the same team, and the object speeds up. If they have opposite signs, they're fighting each other, and the object slows down. That's it. That's the whole game.
All right, we've got our basic toolkit: displacement, velocity, acceleration. Now, it's time to put it all to the test with a classic physics problem, one that brings everything we've just learned together: motion under the constant pull of gravity.
So here's the scene. We've got a tower that's 400 meters high. At the very top, someone just drops a ball, so its initial velocity is 0. At that exact same instant, someone at the bottom throws another ball straight up into the air at 50 meters per second. The big question is, when and where are these two balls going to cross paths? Now, at first glance, these two balls are on totally different journeys, right? One starts high, one starts low. One's moving down, one's moving up. But they share one incredibly important thing: gravity. Gravity is pulling on both of them with the exact same constant downward acceleration. And that is the key that unlocks the whole problem. So, using the language of motion we've been practicing, we can set up the equations for each ball's position. We set them equal to each other to see when they're at the same height, and when you solve it all, you find that the big moment happens after exactly 8 seconds. And at that 8-second mark, where are they? Well, we plug that time back into our equations, and we find they cross each other 80 meters above the ground. It's a perfect demonstration of how displacement, velocity, and acceleration all work together to predict the future. Kinda cool, right? So we've built a really powerful toolkit today. We can now describe anything that moves up, down, left, or right with amazing precision. But all of this was for motion in a straight line. What happens when things get more complicated? What happens when a path curves? Well, that's a question for another time.